Now I'm going to talk about the average value of a function. And uh, honestly, using the word averages, at least if you're in a stats class, that is not a good idea because there is more than one way to figure an average. If you've ever taken stats, you've seen a mean, you've seen a median, you've seen a mode, you've seen weighted means, etc. So let's talk about specifically what we're referring to when we say average. All right, if you want to average some y values, and we're going to call them y values because we're going to try and relate this to a function, but y average, which they will often write as a y with an AVE subscript. If you have a finite number of y values, then we all know how to take an average. And in fact, this is going to be a mean in reality. Well, you just take the first number plus the second number plus the third. You continue until you get down to the last one. Again, because we said that we're going to assume there's a finite number of them. And the subscript n means there's n of them. And you divide by n. All right, pretty easy. We've all done it. You probably averaged your own grades, found the mean of your own grades in this same exact way. All right, but here's the problem. Let's say we had a function that expressed perhaps a temperature over a period of time. All right, now temperature, as you know, is continuous. It can't go from 70 degrees to 72 degrees without passing through 71 degrees. So a temperature curve would be continuous. And if x represents time, and you know what, maybe it would be better to call it a t-axis for time, lowercase t, and maybe it would be better to call this an uppercase T for temperature. Maybe that would be more appropriate. But as you can see on this curve, if you pick points, every single one of those little points represents a temperature, capital T, at a time, little t. Since this thing is continuous, there are literally infinitely many temperatures at infinitely many different times. I mean, if you think that you can say, well, this is time at 1 second, and this is time at 2 seconds, and this is time at 3 seconds, well, what about 1.1 seconds? What about 1.01? What about 3.00006 or something like that? There are literally infinitely many temperatures at infinitely many times here. All right. But if you wanted to, maybe try and get an approximation by saying what's the temperature at 1 second, 2 seconds, 3 seconds, and writing those temperatures down, then you could attempt to do that. So you could look at f of x sub 1, all right, and oh, wait a minute, nope, hold on, I agreed to use a different notation. F of little t sub 1, which would be big T sub 1, that would be your first temperature, plus f of little t sub 2, plus f of little t sub 3. And again, if we're going to do an approximation, it's going to be with a finite number of temperatures. Okay. So plus dot, 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 all the way out to f of little t sub n divided by little n. That would give us an approximation of the average temperature over some period of time. And let's call that period of time time that ran from A to B. All right, so we're looking at the average temperature over this portion of the curve. All right, so if we were to do that, we could do it the same way you figure averages. You figure a mean average of a bunch of grades. Now, let's do a little bit of clever algebra, though, here for just a second. We have previously defined, for integration purposes, we previously defined something called delta x. Delta x was b minus a over n. All right, delta x was b minus a over n. It was literally the width of those little tiny rectangles that you were building, those little Riemanns that we were building back when we were doing integrals by definition. And what I can do here is multiply both sides by n, clear this fraction. So I'll have n times delta x equaling b minus a. I can then divide both sides by delta x. That cancels it here. And I find that another way to write n is a b minus a over delta x. And you may be thinking, well, that looks like a more complicated way to write n. Why would we do that? Well, we'll get to that point. All right, so what I have so far is an average here. And I'm going to replace the n as noted. And I could, by the way, replace f of t, little t sub 1 with a big T sub 1 and a big T sub 2, etc. But I don't want to. Again, I have a motive. All right, so I'm going to replace the n with a b minus a over a delta x. All right, now remember, when you divide by a fraction, you end up reciprocating and multiplying. So when I reciprocate and multiply, I get delta x over b minus a times this sum, this f of t sub 1, plus this f of t sub 2, plus dot, 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 all the way down to the f of t sub n. All right, and what I'm going to do is I'm going to distribute, but I'm not going to distribute anything. I'm going to distribute only the delta x. I'm going to leave the b minus a out here. And I get delta x times f of t sub 1 plus delta x times f of t sub 2 plus dot, 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 down to the end, delta x times f of t sub n. All right, now this portion right here should look familiar to you. All right, not the, ignore the 1 over b minus a. This portion should be familiar to you. This is what we did when we were trying to approximate the area under the curve of a continuous curve with a finite number of rectangles. All right, now if we wanted to, though, make that area become exact, all right, what we could do, and actually this is long-winded and hard to write. Let me do this. This is a summation, so let me write it as such. This is the sum of f of x. Let me use an I. Of I equals 1 to n, 1, 2, out to n. Yep, that's correct. F of x of I times delta x. All right, that's a lot easier to write. Yes, and I is a good choice. I believe it's what we used previously. All right, so again, this is a shorthand notation for an approximation. All right, this part is approximation of an area under a curve. And so what I'm able to do, though, with use of limits is make this approximation become exact. So to make this become exact, I've got a 1 over a b minus a times the limit. Again, to make this approximation exact, I'll take the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I delta x. What that would do, all right, would make this approximation of the average become exact, all right? But again, all of this is now an exact average instead of an approximated average. But this part can be more easily written, all right? The 1 over b minus a, there's really no way to incorporate that other than a 1 over b minus a. But again, this portion of your average calculation can be rewritten as an integral. It's just the integral from a to b of f of x dx. So what we will do is formally define the average value of a function, again, often denoted with an f sub a v e, as equaling 1 over b minus a times the integral from a to b of f of x dx. All right, now that wasn't a super formal derivation, all right? But one way to sort of think about it is, let's say that our function was purely rectangular, right? And had a height of some number, some constant c, and the rectangle was from A to B. Now, if I wanted to find the area under this curve, well, since it's rectangular, area equals length times width. So the area under this curve is the length, which is the b minus a, times the width, which is the c. Well, the c is the height of the function. It is the not only the average value of the function, it's the only value of the function. So it kind of makes sense that the c, therefore, the height of a function, is its area divided off the width. And that's what's happening here. Except if you have a function whose height fluctuates, moving from A to B, then the area, if you found it, would be the integral from A to B of f of x dx. Therefore, the height of the function on average, if there is some line here that is the average height, a point at which sometimes the function's above it, other times it's below it, all right, then it would only make sense that the average value, all right, the f sub a v e as they call it, would be its area divided back off its width. All right, dividing off this dimension should tell us what this dimension is on average. And again, that is how it is, exactly how it is defined. Again, the average value of a function is simply its area divided off its width. That's exactly what it's telling you here. Right? And for that matter, we have a theorem that appears. You've seen the intermediate value theorem, often called the IVT. This is the mean value theorem, which gets a lot of use in calculus. And the funny thing about the mean value theorem, it gets a lot of use behind the scenes. A lot of times, that's what I'm saying is the mean value theorem is being used in situations where you don't know that it's being used. But what the mean value theorem says is that if a function f is continuous on an interval from A to B, then there, smudge those together, there exists a C value, right? And that C is inside, has to be in the interval somewhere from A to B, right? Such that f of C is equal to f average, which of course by definition, this is the definition part, is equal to 1 over b minus a times the integral from A to B of f of x dx. Well, in other words, what this thing is saying is that a continuous function on an interval has to take on its average value. Another way of saying that is that the integral from A to B of f of x dx, which is the area under the curve from A to B, is equal to its length minus an average width. All right? In other words, there is a value, there is a number between A and B, such that if you find the height of the function at that number and multiply it by the width of the interval, that will equal the area under the curve. All right? Again, this says that a function has to take on its average if it is continuous. It has to take on that average value at some point. Now, Got to be careful how you apply this because it applies to continuous functions. So if I was to tell you, all right, I've taken 50 numbers and I've averaged them, 50 test scores perhaps, and I've averaged them, and the average came out to be a 70. Does that mean that somewhere in that stack of papers there has to be a 70? No, it doesn't. Because if you took a stack of papers and you looked at their grades, that's not continuous. That's in fact discrete. On the other hand, if I told you that I drove to Virginia Beach and my average speed was 70, what that means is at some point in time I was going slower than 70. At other points in time I was going faster than 70. And what that also means at some point in time I had to do, at least even for an instant, I had to do exactly 70 miles per hour. Your speed can't average 70 unless you at some point in time did 70. Again, because we're in a continuous situation.